Hi, welcome back, IntroStat students. So today I would like to do the finish up Unit 12 by doing the test, the significance test, hypothesis test, unit test. There are 15 questions, but you can do it. So let's dive in. So okay, let's see if we can do this. All right, let's see. So, are you ready? All set for the unit test? Welcome to the unit test where you get to test your skills for the entire unit. 15 questions, about 30 minutes. Let's go. So, a fast food company advertises, I think, that the pre-cooked weight for its half-pound burger is, on average, 0.5 pounds. And Alvaro is in charge of the quality control test of H naught, which is the null hypothesis, equals to the mean equals to zero point 0.5 pounds, versus the alternate hypothesis, HA, is mu, the population mean, the average, not equals to zero point 0.5 pounds, where mu is the mean weight of all burgers in a batch. So Alvaro took a random sample of 30 burgers from a batch. 30 is a good number because of central limit theorem. It's going to meet the condition where the sampling distribution will be normal, right? Because the sample size is 30 or more, and found that the mean weight, which is the sample mean, right here, this is the sample mean, which is 0.45. Now this 0.45 is somewhat less than the claim. The claim is zero point 0.5, but this is 0.45, 0.49. Is it that much low, so low that you are suspecting that, right? You're suspecting that the null hypothesis is not true. No, we don't know, right? And a sample standard deviation of 0.04. Based on these results, he calculated a test statistic of t equals to approximately negative 1.37 and a p-value of 0.181. Assuming the conditions, there are three, right? The conditions are three. What are they? The first condition is that the sample has to be random. Second condition is that the is central limit theorem applied because the sample size is 30 or more. So central limit theorem is applicable, and therefore the sampling distribution is approximately normal. Are we assuming that the burgers are independent from each other? Okay, cool. So that's assuming that the conditions for inference were met. That what is an appropriate conclusion at an alpha of 0.05? So, right, we need to now know that if your p-value is less than 0.05, then you will reject H naught. Okay, so here is, right, we just said this 0.0181 is more than 0.05, right? The p-value is in fact greater than alpha. Therefore, right, if that's the case, p-value is greater than alpha, we fail to reject H naught, right? We fail to reject H naught. And H naught is, what is H naught? H naught is mu equals to 0.5 pounds. Okay, so with that in mind, let's look at our options. So we are rejecting H naught, which is not true, rejecting H naught, which is not true. So let's look at C and D. We failed to reject H naught. Okay, this is strong evidence that the mean weight is different than 0.5 pounds. That is your alternate hypothesis. So that's not true. We failed to reject H naught. This isn't enough evidence, right? This isn't enough evidence to conclude that the mean weight is different from zero point 0.5 pounds. Ta-da! Okay. it says here, since the p-value of 0.181 is greater than alpha equals to 0.05, he should fail to reject H naught. He doesn't have enough evidence to conclude HA. So, next question. According to a report from the United States Environmental...
Can I get extra credit?
To fail?
Yeah. Hello, Frank.
What are you doing here?
We came to ask if you would like to come to our...
Okay, yeah. Sorry for that interruption. Need to continue. So, according to a report from the United States Environmental Protection Agency, burning 1 gallon of gasoline typically emits about 8.9 kilogram of carbon dioxide, CO2. A fuel company wants to test a new type of gasoline designed to have lower carbon dioxide emissions. That is good. Here are the hypotheses. So the null hypothesis, mean equals to 8.9 kilogram of carbon dioxide. The alternate is less than, right? Less than. So less than 8.9 kilogram, where mu is the mean amount of carbon dioxide emitted by burning 1 gallon of this new gasoline. Under which of the following conditions would the company commit a type 1 error? Okay, so, right, let's review a little bit of what type 1 error is. So type 1, right, type 1 error is, so you reject H naught when H naught is true. So that is committing a type 1 error. So what they're saying is you reject this and you are claiming this, right? So, but then when you claim this is actually not true. This is true. Okay? So type 1 error is you reject H naught when H naught is actually true. So this is what you are claiming, but this is the actual, what is actually happening. Okay? So with that in mind, let's see. So the mean amount of carbon dioxide emitted by the new fuel is actually 8.9, and they fail to conclude it is lower. That's not it, because type 1 error is that you conclude it is lower, but it's not. All right? And they concluded, okay, so this is it. The mean amount of carbon dioxide emitted by the new fuel is actually 8.9. This is actually true, but they rejected it and claimed that it's lower than 8.9. Okay, so see, this is a type 1 error. So H naught is true, but they rejected. Okay, so let's go to the next one. An employee at an aquarium monitors how much their sea otters eat. The amount of food a particular otter eats daily is approximately normally distributed with a mean of 17 pounds and a standard deviation of 1 pound. They suspected this otter was not eating enough, so they took a random sample n days, n equals to 10 days, and observed a sample mean of x bar equals to 16.5 pounds of food per day, to see how likely a sample like this was to occur by random chance alone. So obviously they did a simulation. The employee performed a simulation. They simulated 40 samples of n equals to 10 values from a normal population with a mean of 17 pounds and a standard deviation of 1 pound. They recorded the mean of the values in each sample, and here are the sample means from their 40 samples. There are 40 dots here, and each dot is a sample mean, right? It's a sample mean of 10 values. Okay, so they want to test this. They want to test for the null hypothesis mu equals to 17 pound. So this is 16.8, 16.9, 17, 17.1. So 17 is right here. Right here. And they want to find, so the null hypothesis is mu equals to 17 pounds versus alternate hypothesis is mu less than 17 pounds. So the sample, where is the sample? Based on this simulated results, what is the appropriate p-value of the test? The sample was x bar equals to 16.5. So here, you count 16.5 right here. And how many are there? 1, 2, 3, 4. Now, because this is less than, I need to add this dot as well. So 1, 2, 3, 4, 5. 5 divided by the way, how many dots? 40 dots. And that is my p-value. My p-value is 0.125. Okay, so 5 out of the 40 simulated results were at or below x bar equals to 16.5. Okay, so Fernanda runs a large bowling league. She suspects that the league average score is greater than 150. By the way, that's average, right? Because a perfect game is 300 and half is 150. So she suspects that the league average score is greater than 150 per game. She takes a random sample of 36 game scores from the league data. The scores in the sample have a mean of 156 and a standard deviation of 30. Fernanda wants to use this sample data, to conduct a t-test, all right, on the mean. And this is a t-test because we are using mean. And assume that all conditions for the inference have been met. To calculate the test statistic, all right, calculate the test statistics for Fernanda's test. All right, so here the test statistics, all right, test equals to x bar minus mean divided by, actually, yeah, divided by standard deviation. Okay, and because we are using a sample and we need to use x minus x bar divided by s. So x bar is where your sample have a mean, that's your sample mean, so your x bar is 156, and your standard deviation standard deviation is 30. So, all right, so you should expect that the league average score is greater than 150. So now, random sample of 36. So that's the mean, 156 minus the mean is 150 divided by standard deviation is 30. Okay, so I'm trying to figure out what is the mean and what is the standard deviation, what is the because t statistics is given by this. I know that's x minus mean divided by standard deviation, right? Population standard deviation. This is population mean. But since we're not given population, we are given a sample, right? So it'll be x minus x bar, right? Which is a sample. This is standard deviation. So by right, this is 156, and this is 30, and this one should be 150, right? So what we're going to do is take 150. All right, Fernanda's test wants to use some of the correct assuming, so minus 156 divided by 30. So answer here is negative 0.02. 0 down to 2 decimal place. Oh no. Hmm. Okay. I think I make a mistake, and now I understand why. So my mistake is this. So I know that the t equals to x minus x bar divided by standard deviation is this, has this formula as divided by root n. So if 150 is 150, right, 150 minus 156 divided by 30 divided by root 36. I think it's root 36, isn't it? Let's see. Yes, 36, sample size of 36. Okay. And so it'll be negative 6 divided by 30 divided by 6, right? Because square root of 36 is 6, 30 divided by 6 is 5, so negative 5, negative 6 divided by 5. Okay, so it'll be negative 6. No, that's not, use negative 6. This is negative 6 divided by 5. So, okay, so perhaps it's without the minus sign. Okay, so I think what it is this. The t statistics is x minus x bar divided by sample size, sample standard deviation divided by square root n. And it appears that the mean is actually 150. The sample was 156. And here will be 30 divided by root 36. So do the math, 6 divided by 30 divided by 6, right? Square root of 36 is 6. 30 divided by 6 is 5. 6 divided by 6 divided by 5 is 1.20. All right, so this was my sample mean divided by sigma, I mean mean divided by standard deviation divided by root n. Okay. All right. Next. So a campaign manager. All right. I have to pause this. Okay, a campaign manager for a political candidate released a series of advertisements criticizing their opponent in an upcoming election. Their opponent previously had the support of 45% of voters, and the campaign manager wants to sample voters to test if support for their opponent has decreased. So let P represent the proportion of voters that support their opponent. So, which of the following is an appropriate set of hypotheses for the significance test? So, their opponent previously had a support of 45. So that's your null hypothesis. You're assuming that the proportion is 0.45. So it's your null hypothesis can never ever be anything but an equal sign. So it has to be equal sign, equal sign, equal sign. So in this case, A is out. So it has to be equals to 0.45. Now, what's the null hypothesis? It says that wants to sample voters to test if their support for their if the support for their opponent has decreased. So you are wondering if is it not equals to, or is it less than, or is it greater than? So it's not. It's less than, right? Less than 0.45. right? The null hypothesis has a statement of equality, and the direction of alternative hypothesis less than match their desire to test if support for their opponent has decreased. So Catalina read a report saying that the average daily high temperature in Buenos Aires, which is the capital of Argentina, all right, a few years ago was 18.2 degrees Celsius. Last she believes that last year was warmer than this. To test her belief, she takes a simple random sample of 20 days from last year and record the daily high temperature on each chosen day. So let mu represent the daily average daily high temperature in Buenos Aires last year. Which of the following is an appropriate test set of hypothesis for Catalina's significance test? So this was an average a few years ago, 18.2. So that's equals to 18.2. And she to test it that was warmer, right? She believed that last year was warmer. So it's not equals to, sorry, this is equals to 18.2. This is less than. No, we want more than. Right? Remember the null hypothesis cannot have a more than sign, right? It has to always be equals to. So B and D, they're out. So only A and C. So C is correct because the alternate hypothesis is greater, right? Warmer is greater. Okay, so um, okay, so the mayor of a town read an article that claimed the national unemployment rate was 8%. They suspected that the unemployment rate was lower in their town. So they took a random sample of 128 residents to test. Okay, here the null hypothesis is the mean is 0.08 because it's 8%, right? The proportion of an unemployment versus the alternate hypothesis where the proportion is less than 0.08, where P is the proportion of residents that are unemployed. They found that 6 residents in the sample were unemployed, and the article corresponding test statistics was Z equals to approximately negative 1.38. Assuming that the necessary conditions are met, what is the appropriate p value for this significance test? So, um, so we need to understand this. So here, right, the mean is 0.08, and they found so z goes to negative 1.38. Um, so we are now looking at a standard normal. Standard normal is here is 0, and here is negative 1.38. Okay, so now which direction am I going to shade? Am I going to shade to the left or right? It all depends on your alternate hypothesis. So this is less than, it's pointing to your left. So this is your p-value, this little area here. So there is a calculator function. Okay, it's normal CDF, and there are 4 things we need to put in. All right. So the lower bound, this is going to negative infinity. So in a calculator that doesn't have infinity sign, so we need to put negative 9999, as big as a number you can, but you have to put a negative sign in front. And then here is negative 1.38 because that's the upper bound, right? So this is lower bound, this is upper bound, negative 1.38, and the mean is 0, standard deviation is 1. So what we do is, how do we get to normal CDF? Second vars. You see normal CDF number 2. Now the lower we said was negative 9999, and the upper was negative 1.38. Mean is 0, standard deviation 1. Ladies and gentlemen, that is your p-value, and we want to round this to the nearest three decimal place, 0.084. So that's three decimal places. All right? Okay. Okay, we're halfway through. Ellie read an article claiming that 10% of people in her country were senior citizens, and she thought, right? She thought that it may be higher for residents in a city. She took a random sample of 225 people from her city and found that 36 of them were senior citizens. Um, she wants to test the null hypothesis is that proportion p is what p is the proportion of people in a city that are senior citizen. So they want to test that p equals to the standard, the mean, the national average is zero point 0.1 versus she thinks there are more, right? They may be higher, right? She thought that it may be higher, so more than zero point 0.1. Assuming that the conditions for inference have been met, calculate the test statistics for Ely significance test. So, right, the test statistics z is x minus mean divided by standard deviation, and mm, we're not using x, we're using p. P p hat minus p divided by, the formula is p times 1 minus p divided by n. Okay, so p hat was what? You have found that 36 of them were senior citizens. So that's your p hat. 36 divided by 225. Right? So to put it all together, right, p hat is 36 divided by 225 minus p, we assume p to be 0.5, 0.1, sorry, 0.1 divided by square root of 0.1 times 1 minus 0.1 divided by n is 225. Okay, so let's put all of this together. There's a way to do it on a calculator that is actually going to work quicker that way. So what I'm going to do is put bracket. I'm going to put the p hat first, which is 36 divided by 225 minus away 0.1 divide by, I'm going to put two brackets. First bracket is right, I need to find out the p, which is 0.1 times 1 minus 0.1, and then divide by the sample size n, which is random sample 225, right? N is 225. 225, and we'll close the bracket. So because of this open bracket, I need to make sure that I close this. I already did. Okay. Maybe I'm not doing this right. So let's do this. So 36 divided by 225 is 0.16. So 0.16 minus 0.1, which is that. Then we need to divide by, I did not do the square root. So square root of 0.1 times 1 minus 0.1 close bracket divided by 225, and then close bracket. So 3. Okay. So Jamarian was testing H naught equals to mean equals to 45 versus alternate hypothesis is mean less than 45 with a sample 5 observation, right? Sample n equals to 5. His sample mean was 40 and his sample standard deviation was 3. Assume that conditions for inference were met. Which of the following um, so we need to find, okay, so this is obviously a t-test, right? Because we're dealing with me. So t-test, and this is less than because of this, right? It's less than, and we, so with 4, so the degrees of freedom is n minus 1. So here is 5 minus 1. So the degrees of freedom is 4. And the formula is x bar minus mu divided by mm, okay, by standard deviation. Okay, so but then because we don't have population parameter, we have sample. So we're going to change everything to sample, which is x minus x bar divided by s divided by root n. Mm. Okay, so the mu we actually know mu is 45, and the mean was 40, right? The sample. So this is your sample. So what we're going to do is this. So sample mean is x bar minus the population mean divided by s divided by root n, right? Because we don't have this, that's why we're using t distribution. So we're going to use the sample standard deviation divided by root n. That's the formula. So we're going to have x bar is 40 divided by mean is 45 divided by standard deviation is 3 divided by root n, which is 5. So it looks like so this is greater than, we don't want that, greater than, we don't want that, we want less than. All right, we want less than, and we don't want degrees of freedom. It's not 5 because it's 5 minus 1, so it's 4. So Asha owns, need a drink. Asha owns a car wash and is trying to decide whether or not to purchase a vending machine so customers can buy coffee while they wait. She'll get the machine if she is convinced that more than 30% of her customers would buy coffee. She plans on taking a random sample of n customers and asking them whether or not they would buy coffee from the machine. She will then do a significance test using an alpha of 0.05 to see if the sample proportion who say yes is significantly greater than 30%. Which situation below would result in the highest power for the test? Okay, this is always interesting because, right, so the null hypothesis is that that we are assuming, right, we are assuming that 30%, right, 30% customers would buy coffee. The alternate hypothesis is that we are assuming that there's more than 30%. She's planning on asking them to see, okay, so, and the alpha is 0.05. Now, Alpha is alpha is actually a type 1 error. Okay? And power, ladies and gentlemen, power is 1 minus um, 1 minus beta, right? Highest power is type 1 error is alpha. Okay, type 1 error is alpha. Power is 1 minus beta, and beta is 1 minus alpha. So in this case, if we want the highest power, we need to have a low um, beta, right? Highest power comes from the fact that if we can make beta low, right, as low as possible, then the power will be as big as possible. So now, but then if we look at beta is 1 minus alpha, which means if I need beta low, I need alpha high. Okay, so in order to have high alpha, let's look at what the options are. She used a sample size of n equals to 100, n equals to 200, n equals to 50, and n equals to 200. Um, so we need a small, what is it in this case? We need, what situation below would result in the highest power? And in order to get a highest power, we need power is 1 minus beta. So alpha is 0.05. So we need to make sure that we will have to reject that. Okay, so it's either B or D, and we need to reject. So here, she uses a sample size of n equals to 250% of all customers would actually buy coffee, because 50% is relatively far above 30%, and 200 is the largest sample size given. So here are two different samples drawn from two different populations. So sample A, n equals to 11, sample B, n equals to 14. So do you see how sample A, there's a gap here, so to speak, and sample B, it's more skewed to the right. Which samples satisfy the normal conditions? So since both n are really, really small, and this is already skewed to the right, and there's a gap here for both for sample A, so it doesn't look like neither sample would work. So a campaign manager for a political candidate released a series of advertisements criticizing, we did this earlier, kind of, where the opposing candidate previously had the support of 45% of voters, so the manager wants to test H naught equals to P equals to 0.45 versus alternate hypothesis P is less than 0.45, where P is the proportion of voters that support the opposing candidate. After running the advertisements, the campaign manager obtained a random sample of 500 voters and found that 220 of those sample supported the opposing candidate. The resulting T statistics is negative. Z statistics is approximately negative 0.45, and a P value is approximately 0.33. Assuming the conditions for inference were met, what is the appropriate conclusion at alpha? So P value 0.33 is more than 0.05. So if it's p-value more than alpha, we fail to reject, right? We fail to reject the null hypothesis. So in that case, we uh, exactly, well, we cannot, okay, we can conclude that less than 45. No, we can't do that because we have to say that. We have, that's the null hypothesis, and we cannot reject. We didn't have enough evidence to reject it. So they can conclude, they can conclude, they cannot conclude. They cannot conclude. Okay. So they can conclude, right, that exactly 45% of voters support the opposing candidate, which is what we're saying. We cannot reject H naught, and H naught is apparently right here, exactly 45. I'm not. Okay, it's crazy. Let's see. P-value is more than alpha. If p-value is more than alpha, we cannot reject. We fail to reject. Fail to reject 0.45. So we cannot conclude. That's. I thought that's what I did. We cannot conclude. I meant to say this. Crazy. That was what I wanted to say. We can't conclude that less than 45 because, look, we are concluding this. We have no evidence to suggest this, right? So we cannot conclude that the proportion is less than 0.45, which is what I wanted to say. We cannot conclude that less than 45% of voters support the opposing candidate. I don't know why that didn't work. So a ketchup company regularly receives large shipment of tomatoes. For each shipment that is received, a supervisor takes a random sample of 500 tomatoes to see what percent of the sample is bruised and perform a significance test. If the sample shows convincing evidence that more than 10% of the entire shipment of potatoes is bruised, then they will request a new shipment. So if we have evidence, showing that there's more than P is greater than 10%, then we will reject. So let P represent the proportion of tomatoes in a shipment that are bruised. What are the appropriate hypotheses for the company significance test? So null is that it is 0.1, right? It's 10%. And the alternate is more, right? Alternate is more. Okay, alternate is more. Okay, all right. So 14 out of 15. So I got two more. Louisa wants to go on a popular talent TV show. In order to be accepted, her audition must get at least 60% positive votes from the people in the crowd. She was afraid she would not get enough votes, so she made a video of her act and showed it to 60 random people from the crowd before the show. 50% of the people said she would vote for her. So 50% of 60, that's about 30. Well, and it's only 50%. She needs at least 60, right? Right, to be accepted. Let's test the hypothesis that the actual percentage of positive votes among the crowd is 60% versus the alternative that the actual percentage is lower than that. The table below sums up the results of 1,000 simulations, each simulating a sample of 60 votes, assuming that there are 60% positive votes. According to the simulation, what is the probability of getting a sample with 50% positive votes or less? So 50% of positive vote or less. So I need to take 89 plus 24 plus, I got 1 here. Okay, and the p-value would be, because I need to, how many people? 1,000. If I divide that by 1,000, that would be my p-value. All right, so what is the probability of getting a sample, which is 0.11 let's agree that if the observed outcome has a probability less than 1% under the tested hypothesis, we will reject the hypothesis. So the observed outcome has a probability less than? No, it's actually more than 1. So how many percent is that? 114 divided by 1000 is, yeah, it's about 11%. So if it's less than, we reject. So we are not rejecting, we cannot reject. So I believe this is the last. Quintin read a report claiming that 4% of police officers in the US have had a formal complaint filed against them. Quintin suspects that this figure is higher in his state. He obtains a random sample of records for 500 officers from the approximately 20,000 officers in the state. He wants to use this data to test p equals to 0.04 versus p is greater than 0.04, where p is the proportion of officers in Quintin state who have had a formal complaint filed against them. Which conditions for performing this type of significance test have been met? So there are 3 conditions. So first of all, is that random? Okay, that's random. And expected number of counts and expected counts of successes and failures are significantly large. So we have to use this formula, right? It's the formula for that is n times p has to be greater or equals to 10, and n times 1 minus p is greater or equals to 10. So this is for successes, and that's for failures. Okay, so n is 500. We know n is 500, and p is 0.04. Okay, with that in mind, 500 times 0.04, greater than 10. And then we take 500 times 1 minus 0.04 is also greater than 10. So the expected counts of successes. Oh, you walked in.
Yeah, I just flashed my badge and said, VIP.
Okay, I'm finishing something here. The individual observations can be considered independent.
What? Independent observations?
Well, yeah, I'm doing a recording. So those 3. Yes, great work, guys. Thank you very much. We'll end this video.